Hi everyone, this is the first video of our self-paced learning material for Lecture 7. There are 4 videos for this tutorial and you can track the order of videos by looking at the lecture code. For example, this video is Lecture 7a. So in this lecture, we will look at how energy is transferred as heat in the course of a chemical reaction. Okay, so let's start by defining thermochemistry. So thermochemistry is the study of heat released or absorbed in a chemical reaction or physical processes. Now, thermochemistry is a branch of thermodynamics because the reaction vessel and its contents shown in this slide form the system. And secondly, the chemical reactions result in the exchange of energy between the systems and the surroundings. So, what basically are the objectives of thermochemistry? First, when we study chemical reactions, we want to determine and calculate the amount of heat that is evolved or absorbed during a chemical reaction. In some chemical reactions, the reactants absorb heat energy from the surroundings to form the products. These reactions lower the temperature of the surrounding area, thereby creating a cooling effect. In this case, the system absorbs heat from the surroundings. These reactions are actually called endothermic reactions. Endothermic reactions can also be described in terms of the change in enthalpy or delta H. The simple enthalpy diagram for an endothermic reaction is shown in this slide. Recall from your previous chemistry courses that the activation energy, EA, is the energy that must be provided to the reactants so they can overcome the energy barrier and react. In endothermic reactions, the enthalpy of the products is higher than that of the reactants. Now, the gap in the energy accounts for the energy that was absorbed by the system during the chemical reaction. The enthalpy change in the reactions is also called the heat of reaction or delta H reaction. This is equal to the enthalpy of the products minus the enthalpy of the reactants. Now take note that the signs of the delta H refers to whether heat is absorbed or released in a chemical reaction. Considering endothermic reaction, delta H must be positive. This means that the heat is absorbed by the system. In contrast, reactants in some chemical reactions release heat energy from the surroundings to form products. These reactions increase the temperature of the surrounding, thereby creating a warming effect. These reactions are called exothermic reactions. We can follow the course of an exothermic reaction using the diagram shown in this slide. The enthalpy of reactants is higher than the enthalpy of the products. The gap simply means that the heat is given out to the surroundings. When a chemical reaction releases heat, the products formed, that is, the system at the final state, will have less enthalpy, and as a consequence, the change in the enthalpy will be negative. The second objective of thermochemistry is to provide information about bond energies. Now, we've learned in your past chemistry courses that all chemical reactions involve breaking of old bonds followed by making of new bonds. Along these processes, heat is absorbed or released in the reaction. We can think of a reaction as a process in which the bonds of the reactants absorb energy when they break, as shown in the left part of the slide, and the bonds of the products release energy when they form, as shown on the right part of the slide. In summary, to break a bond, the system must absorb energy, which is an endothermic process. Conversely, when a bond is formed, the energy is released to the process, which is an exothermic process. Now, depending on the overall change in the enthalpy, the process will be exothermic or endothermic. Recall from our previous lectures, there are 2 types of heat transfer, one that occurs at constant volume and another that occurs at constant pressure. These 2 energy transfer processes are related to 2 thermodynamic functions such as internal energy and enthalpy, respectively. Now, the magnitude of heat of reaction occurring at constant pressure and constant volume are in general different. Recall that the heat of reactions are related as expressed in the following equation, which we have previously derived from the definition of enthalpy. That is, delta H is equal to delta U plus delta PV. Now, the PV term can be replaced by the ideal gas equation PV is equal to nRT, leading to the following expression: delta H is equal to delta U plus delta N gas times RT. In this equation, take note that the delta N gas is the change in the amount of gas molecules in the reaction, which is given in this slide. This is an important equation in thermodynamics as it relates to change of enthalpy to chemical reactions that produces or consumes gas in a chemical reaction. Okay, so let's try to consider this example, okay? So the change in the enthalpy for the combustion of 1 mole of benzene is negative 3,267.6 kilojoules per mole at 298 kelvins. So we're asked to calculate the delta U for the reaction, and the reaction is given in the slide. So we start off by noting the relationship for the change in the enthalpy of the reaction that produces or consumes gas, and this formula is given in this slide. Delta H is equal to delta U plus delta N gas times RT. Now, the first thing we have to do is obviously to substitute all the values to the equation. So this one gives us negative 3267600 joules is equal to delta U plus 6 minus 15 halves times 8.314 joules per mole Kelvin times 298 kelvins. Okay, so solving, okay, the change in the internal energy is now calculated as negative 3,263.9 kilojoules.